electrochemistry and bonding. So that would include, was electrochem and bonding? Kinetics and bonding. It was kinetics and bondings. So you were supposed to be working on kinetics and bondings, which review 24 basically and following. Are there any particular ones you'd like me to go over? Any questions that we haven't done? 29. Let's take a look at 29 here. 29, answer the following questions about the element selenium. Ooh, this is a good one. This was the 2000 test. In fact, this one, by the way, was on my last year AP Chemistry final. So speaking of the final is next time, so be prepared. All right, samples of natural selenium contain 6 stable isotopes. In terms of atomic structure, explain what those isotopes have in common and how they differ. Basically, if you know what an isotope is, so selenium is the element Se, and there are 6 isotopes. What's that mean? Anybody? Yeah. Same protons and electrons, and they have a different number of neutrons. Remember with our unit on nuclear chemistry, you could have Se. Now if I look on the periodic table, he looks like he weighs 79, but there's probably Se 80. I don't know what the specific ones, they didn't tell us. And there's probably Se, 81. What's the difference between 79, 80, and 81? Just the number of neutrons, which changes its mass, right? So it's just understanding the definition of an isotope. So the thing that's interesting about this question, just as a side note, and this is something I've noticed over the recent years of the tests, this question is really not a bonding structure intermolecular force question, is it? This question A is a nuclear chemistry question, right? So they kind of throw in some, they're kind of beginning to, it used to be the questions were so topical that it was all bonding, or was all equilibrium. Now they're kind of throwing in a few other topics kind of surreptitiously. It's mainly bonding, certainly. Write the complete electron configuration for the selenium atom in the ground state. Indicate the number of unpaired electrons in the ground and explain your reasoning. So it's for selenium. So we're just going to read the periodic table like a book. It'll be what? 1s2, that takes me to helium, right? And it'll be 2s2, that takes me to beryllium. And it'll be 2p6, and that takes me to neon. And then it'll be 3s2, good, that takes me to magnesium. And then it'll be 3p6, and that takes me to argon. And then it's going to go 4s2, and that takes me to calcium. And then it's going to go 3d10, takes me to zinc. And then it's going to be 4p4. But that's not the full question. Read the question carefully. It says, indicate the number of unpaired electrons in the ground state. What are they referring to? This last level, if I were to draw it in the box notation, when in doubt, draw the box notation. This is the 4p level. What's it going to look like? 1, 2, remember they split up before they double up, 3, 4. How many unpaired electrons? 2 unpaired. If you draw this and say 2 unpaired, you'll probably get full credit, because you're showing that you know this, and this is the 4p orbital. Pretty easy question, right? Question C, in terms of atomic structure, explain why the first ionization energy of selenium is less than that of bromine. Okay, so we got selenium and we've got bromine. Okay, so you've got selenium and bromine, and this one is smaller, right? And this is higher. What does that mean? Why does bromine have a higher ionization energy than selenium? Now, what's ionization energy, again? Energy to remove an electron. Excellent, Jamie. All right, so that's the energy to remove an electron. So, and what's the trend as you go across the periodic table? As you go across, they get higher. Remember, top dog is helium. He's got the highest ionization energy of anybody. So you would expect bromine to be higher, right? Now, you can't just say, because of the trend, is that as you go across, they get bigger. They're not going to accept that. Remember, it always comes down to size. What's true about bromine? Bromine is not bigger. Bromine is smaller. If you draw selenium and bromine, this is selenium and this is bromine, if you will. Because selenium, they have the same clouds, right? Remember, as you go across a period on the periodic table, as you go across, they get smaller, right? Why do they get smaller? Because you're in the same cloud, the same, as we'll say in quantum mechanics, the same principal quantum number. And as you go across, you are also adding what? Protons. Or increasing the nuclear charge, the charge of the nucleus. So that causes the electron cloud to shrink. Well, it's going to be harder to move an electron that's closer. It's just this whole magnet thing, right? If something is closer, it's harder to remove it. If you have opposite magnets, they got more strength if they're closer together, right? So it comes back to size. But then you got a bit of an interesting question, don't you? That's question I. Question II says greater than that of tellurium. Oh, never mind. Then that's not so bad. So you've got selenium. I thought they were going to ask a different question. Never mind. And tellurium. Why is this one higher? Because it's smaller. Here's selenium, and this is tellurium. Because what's the difference in tellurium? Because he's got a whole nother level of electrons to hold on to, doesn't he? Okay, now don't just say because it's smaller. You'd probably get half credit. You have to explain it is smaller due to the fact that you have an additional electron cloud. That's kind of the key on that. So keep in the back of your brain. Saying it's smaller is you're going to have to get more detail. If there's detail, add it. If you know, and if you've said more than you need to say, they're not going to take it off unless you say wrong things. Okay, don't say that it's bigger or it's got less electrons, therefore it's bigger. I mean, you know, you've got to say things that are correct, otherwise they kind of get testy. Okay, letter D. Selenium reacts with fluorine to form SeF4. Now, I have not even read the question here, but I see SeF4, and I'm guessing, you know what I ought to do? Probably draw the Lewis structure. I think they're going to ask me to. Sketch the molecular. Okay, draw a complete Lewis. Okay. Even if they didn't ask, I think you should. Well, it's SeF4. So Se's got 6 electrons, plus 4 times 7. So 7 is 28, and 6 is 34. You got 34 electrons, so Se, 2, 4, 6, 8. Now I'm going to be lazy. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 33, 34. Don't put the little lines on there. Those two lines. Those lines represent 2 electrons. When you do this in the AP test, don't do that. All right. What do they want? They want to know the geometry. Oh, it's my favorite shape. What shape is this? This is a seesaw, isn't it? I love the seesaws. Okay. Indicate whether the molecule is polar or nonpolar and justify your answer. Is it polar or nonpolar? Polar. Because the C shape, you see, in a seesaw shape, you're going to take off. It's going to be here, 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 and here, where this is coming out of the board at you, and this is behind the board. Because if you're to draw the polarity, because there's this extra pair of electrons right here, what's going to happen is it's going to be like this, isn't it? And I think drawing it like this, or maybe if you were to do this on here, I would draw it like this, where this, I did that wrong. The arrow goes the direction. This would be the positive end, and this is negative. Sometimes, remember we did that when we did polarities? If you draw an arrow like this, and you put a positive, this goes to the positive end, and the arrow goes towards the negative. The fluorine is going to, because it's very electronegative, is going to draw the electrons closer to the fluorine and make this side positive and this side negative. It's like saying this side here is positive and this side here is negative. So you have to justify why is it polar. Honestly, this arrow with this little cross at the back basically almost does the whole thing. Good? So that's not a terribly hard question, is it? This question 29. If you get this one, you'll be happy with that one. A's a little tricky, isn't it? That's the thing that may be new. Yeah, and that's all right. We've got to learn how to do those. Yeah. 28C. So that'd be the previous one. So if we go back and do 28C. All right. Explain according to the, okay, we got calcium is bigger than zinc. All right, both calcium and zinc are in the same period on the periodic table. They're both in the 4th period, right? Well, what's the general rule as you go across the periodic table? They get smaller. Okay, but why? As you go across, you get more protons, right? And you have the same cloud. All right, now granted, it's 3s or 4s2, 3d10 versus 4s2. But remember, 3d, the 3 represents the distance from the nucleus. It is higher in energy, but it's lower in diameter. And so if you were to maybe think of it this way, here's calcium with his electrons, and he's got 20 protons, and he's going to have 20 electrons, right? And then the zinc is going to be smaller because he's going to have 30 protons, and he's holding on in the same cloud to 30 electrons. But he's in the same cloud, right? And the D's fit inside of the 4s. So it's going to cause this to shrink. Good? Other questions? He's got a higher positive charge, but he's holding, even though he's holding on to an equivalent number of electrons, the electrons are in the same cloud, which is going to cause it to shrink as you go across that table. Did you guys get question D? I think is actually the more challenging question on this one. Boron has a lower ionization energy than does beryllium. So it goes from beryllium and you go to boron. Now, remember, helium's top dog, and so as you go across, you would expect boron to be higher than beryllium, wouldn't you? But they're saying that actually it's the reverse. This one is higher. How come? We talked about this last time, but real briefly. Because beryllium is full. That's exactly right. You see, beryllium, in fact, don't just say it's full. Draw the structure. For beryllium, it looks like this. And for boron, this is the 2s orbital. It's 2s, and you got this full, and then you've got 2p. See, he's just got one extra electron hanging out in 2p. It's a lot easier. Remember, half or full orbitals are very stable. And so this is going to have a slightly lower ionization energy than the beryllium because it's easy to remove this one electron who's just hanging out by himself. Does that make sense? Draw these structures here, and that will make everything a better deal for you. Good? Jamie, you're looking confused. You're just tired. Okay. Good? Yes, no? All right, we have 2 more to cover today, and then we are going to be done with the review. The one thing I do want to spend some time on at some point, probably next week, is we have really not talked in detail about multiple choice. But, I mean, by doing the free response, you are learning the multiple choice topics, if you think about it, and also doing your note cards and all that kind of stuff as well. So the last section of real content that we haven't covered is colligative properties. And solutions. All right, this is a very quick section to talk about for us today, not very long on this. What is a colligative property? There are 4 colligative properties. There is freezing point depression. There's boiling point elevation. There's vapor pressure lowering. And there is osmotic pressure lowering. What does colligative mean? You may remember what the colligative is. When you add you have a solution, but these properties depend only on how much. Depend on what or how much is dissolved, not what is dissolved. Frankly, you only really care about 1, 2, and 3. I've never seen osmotic pressure on the AP Chem exam, so let's not worry about that one. Freezing point depression, it actually all comes down to the fact that it lowers the vapor pressure. There's that classic question you had on the last test, I believe. You had a beaker. This one was filled with salt water. In another beaker, it was filled with water. And it was in an enclosed bell jar. This kind of explains everything. And so you put a seal over the top, what happens? All of the water moves into the salt water. Why? if you have a vapor, what's vapor pressure? Vapor pressure is the pressure exerted as the liquid evaporates, right? You stand at the gas pump and you smell the gasoline. It's because the gasoline is evaporating. It's creating a pressure, a vapor pressure, okay? If you walk into a room and a gal's been put some perfume on her and you can smell her perfume, the liquid perfume has evaporated and turned into perfume gas, and now you can smell it. It's created a vapor pressure. But solutions have a lower vapor pressure than do pure solvents. So pure water has a high vapor pressure, or higher, and this has a lower vapor pressure. So that means this is going to evaporate faster, right? This is also going to evaporate, but eventually it's also going to reach a condensation. And so the picture at the end is going to be this beaker will be full and this beaker will be empty. Okay, this then relates to ternary phase diagram. What ternary phase? What are you talking about, Mr. B? When you get these tend to be multiple choice questions. These questions where this right here is pressure, and this is temperature, and this is a solid, this is a gas, and this is a liquid. You love these questions where you get the triple point and all that kind of stuff. We played around with that. Okay, this right here is the vapor pressure line of a pure substance. If I were to draw that vapor pressure line, so if I zoomed in on that line, well, we'll just draw it on this one. What would it look like if you had a solution? Instead of having water, you had salt water. This would look like this. It would be lowered. But what do we also learn about this line? What does this line here represent on the black line, not the red line? Oh, here, I've got the lights on and you guys aren't talking to me. What is the black line and the red line? The black line represents what? The pure substance, right? Let's say water or whatever. Well, water would have let's call this carbon dioxide. So this would be pure water, right? But this line here, what is true about what's happening is you cross this line, what happens? You go from a liquid to a gas. It's going to boil, right? But it's going to boil at a different temperature if you cross the red line versus the black line, right? So therefore, the boiling point is higher, and actually the reverse, the freezing point then is also lower, right? So freezing point and boiling point are the ones they emphasize. So if you have water, water's your classic example. Water freezes at 0 degrees, right? And it boils at 100 degrees, right? But if you have a solution, guess what? That's at 0 degrees. It's going to freeze here at minus 10 degrees or whatever. It varies, right? And it's going to boil at 106 degrees or something like that. I don't know. Then there's, of course, an equation that tells us how we can calculate what that is. And what's that equation? Delta T equals IKF times the molality, or delta T equals IKB times the molality. The K thing here, this is a constant. And, of course, the little m is the molality. And the I, what's the I? It's the Van Hoff factor. What's that mean? This is the number of ions that it breaks apart into, right? So for salt in ACl, I equals 2. For magnesium chloride, I equals 3. And for glucose, C6H12O6, I equals 1. Because it doesn't break apart because it's molecular. It's not ionic. Molecular things won't break up. Good? So remember how to do this? Now, typically, they do not ask you to solve for the freezing point. They don't ask you to solve for delta T. Almost always, they're going to ask you to solve for the molar mass. Because delta T, it's easy to measure. We did this, right? We did this lab, and we found the molar mass of isopropyl alcohol, if you recall. We had isopropyl alcohol, and we dissolved it in water, and we froze it, and we found the change in temperature, and we found the molar mass. That's typically the way these questions look if you get a problem on the AP Chem test. So, okay? There's a couple of sort of conceptual questions, and there's sort of more free response type questions. So let's take a look at some of these questions found. Let's do the conceptual one first. Question number 2033, the 2001, no, let's do the 1999 test, pardon me, 32. So open up your packet to question 32. Now, There's a number of different questions, but they all kind of relate. Which solution is the highest, no, it's probably lowest, I can't read here, the lowest electrical conductivity. So we've got 4 solutions, and they're all, what do you notice about their molarities? They're all the same, right? They're all 0.1 molar. So the difference is in what it's made of. We have NaF, MgCl2, what's this one called? C2H5OH. How many carbons? 2 carbons. My elephant plays basketball, so E for ethanol. So ethanol. This is ethanol. This is the alcohol that's put in beer and wine and that kind of thing. And what about this one? He guesses it's got a COOH. It's hard to read. CH3 COOH. You know what that is? How many carbons? 2. And you've got the OOH. This is ethanoic acid. Because it's actually going to look like this. CC double bond O OH. And then there's H's here. Okay, anyways, which one has the lowest electrical conductivity? Explain. Who is the lowest electrical conductivity? Huh? The acid is incorrect. It's the alcohol. All right, so the answer to A is C2H5OH. Why? I equals 1. It won't dissociate at all. It won't dissociate. Does the acid dissociate? What kind of an acid is it? It's got to be a weak acid. Why is it a weak acid? Because it's not one of our 6 strong ones. If you have an acid, it has to be a weak acid, doesn't it? So it's going to partially dissociate, isn't it? In fact, this is better known as what? We've used this acid 100,000 times this year. Well, there's a more common name instead of ethanoic acid. It's also called, you know, what is this also called? You guys, you've seen this written in a different way. HC2H3O2. Same thing. Acetic acid, that's correct. So it has a partial dissociation, right? So that's the answer. Which one has the lowest freezing point? So you're looking for the one where, what do you want there? Which one is the lowest freezing point? The mag chloride or magnesium chloride. Why? Because I equals 3. Delta equals I KF times M, and this is going to be 3. Since the molality will be roughly the same, they've given us a molarity, but I think, you know, molality and molarity are pretty close. There's some slight differences. All right, which one will have the greatest vapor pressure, right? Actually, and you need to explain by talking about I equal to 3 or the Van Hoff factor. So which solution is the pressure of the water vapor greatest? Phenol jumbo 1. All right, this is going to be Raoult's law. All right, when you talk about water, we can write this down later, but the total pressure will be the mole fraction of the water times the partial pressure of the water, right? So which one has the highest number of moles of water compared to the rest? I'm thinking about myself here. Hold on. What would I be for acetic acid? Like 1.1. See, this is 1.0. This is 3, and this is 2, right? What do you think about that one? I'm pretty sure that it's going to be the one that it's going to be the ethanol one too. This one I have to sit and think about because it could also have, it might be the one with the lowest molar mass, but these you have to multiply by 2 and 3. Yeah, it's got to be the ethanol again. And letter D, which is the highest pH? No, an acid is going to have a low pH. Which one is it? NaF is correct, because now if you have NaF, what do you care about? Na is the cation of a strong base, sodium hydroxide. Fluoride, though, is the anion of a weak acid. So if you take F negative plus water, you're going to make HF plus hydroxide. This is an acid-base question right here. And that's how you would explain it. You write this reaction, you've explained it. This is going to have the lowest pH because it's an acid. But this is why is magnesium chloride? Why didn't count that one? Because Mg, his partner is MgOH, so it's pretty much a strong base kind of in the border. And then chloride is like HCl, and of course we know that to be a strong acid. So you can see how those two aren't going to count. So if you could draw this reaction, you would be perfect to answer that question. Not horrible, is it? The question of the day, most definitely, I would guess, will be a question something like this one. I have seen this type of a question. Hold on, maybe not this one. That's an acid-based lab. I'm looking for a math one. No, I want 31. I'll stand corrected. I want the 31 question. Here it is. All right. If I have seen this question once, I've seen it a dozen times on the AP Chem test. This question is really not terribly difficult. With an unknown compound contains only carbon, hydrogen, and oxygen. A pure sample of the compound is analyzed, and we get some percentages. Determine the empirical formula. What's our little pneumatic memory thing? Percent to mass, mass to mole, divide by small, times to whole, right? Got to have that memorized. All right, letter A. Determine the empirical formula. There's no colligative yet. So I've got carbon, and the carbon is 65.60 grams. That's a percent, but I can kind of just quickly convert that to grams. And then the hydrogen, it's just C and H, isn't it, is 9.44 grams. All right, so divide by 12 grams per mole. And then there's oxygen, which will be the remainder of the percentage. This is 9.44 moles. And then 65.6 divided by 12 gives me 5.47 moles. All right, so my percentage is 65.6 plus 9.44. Subtract that from 100. And for my oxygen, I get 24.96 grams. Divide that by 16 molar mass of hydrogen, or oxygen, pardon me, and I get 1.56 moles. What do I do now? Divide by small, right? 1.56, 1.56. This, of course, is 1. This will be 6.05. 5.47 divided by 1.56, and this will be 3.5. What do I do now? Times everything by 2, so this will be 7, 12, and 2. So the empirical formula will be C7H12O2. Got ringing bells? If you not get nice, pretty numbers, then you've done some math and go back and fix it. This can't be that difficult. All right, so C7H12O2. All right, so that was question A, C7H12O2. So I've written down. All right, it says a solution of 1.57 grams of the compound in so many grams of camphor does it freeze at a certain temperature below the normal freezing point. La-di-da-di. The normal freezing point depression constant for camphor is this number. What's the molar mass? All right, first of all, it's a molecular compound, so you use the equation delta T equals I Kf times M. What is the I going to be? It's 1. And the Kf, it's a constant. They gave it to us, looks like. They said that it was 40. All right, watch that. The units on that are, I thought that's a very large number. But it's 40.0 kilograms, watch that, Kelvin per mole. So So we're going to have to convert this to kilograms. All right, that's fine. Times the molality. And then what is the change in the freezing point? They say the change in the freezing point, it went 15.2 degrees below the normal freezing point. So that's 15.2. So now I'm going to solve for my molality. 15.2 divide by 40. Actually, that makes sense because it's moles per kilogram. Right? Yeah, that makes sense. So the molality is 0.38 molal. Now, we know, by the way, by the molar mass, I said this earlier, we probably should have. Molar mass is grams per mole, right? What are the grams? They gave it to you. What is it? 1.570, right? So if I had the moles, I could plug it in, I get my answer. So this molality is going to get me the moles. So if I have 0.38, now watch how I do this. I moles per 1 kilogram. How many kilograms of stuff did I dissolve it into? 16.08 grams, so that's 0.016, you rock, man, 08 kilograms. Kilograms cancel, and what do you get? I get 0.39, 6 moles. So then this goes here. Did I do something wrong? Oh, I added it. Hold on. My calculator, I just looked at my, that's the 0.38 times 0.01608, I get 0.006. Hold on. 1. 0.00611. So 1.57 divided by my previous answer, I get 257. Good? That's the answer to B. These are a little tedious, these questions, aren't they? Anything else I need to do? Did they ask me for the molecular formula? All right, the apparent molecular formula, because basically the C7, what does this add up to right here? C7H12, so 12 times 7 plus 12 plus 16 times, usually they ask that question, this is 128. This needs to be a factor of this, right? What's 128 times 2? 256 or 257. We're close enough. So the real formula is going to be C14, got to double it, right? H24O4. Good? Does that make sense? All right, that's just B. This is a long Louise. When 1.57 grams of the compound is vaporized at 300 degrees Celsius in 1 atmosphere, the gas occupies a volume of 577 milliliters. What is the molar mass of the compound based on this result? All right, what have they just given us? They've given us a bunch of information that gives us into Pivnert, right? Well, what's molar mass again? It's grams per mole. What did they just give us? What's the mass? Isn't it 1.57 grams? In Pivnert, you've got N, don't you? Can that N then be plugged into here? I'm hoping we get 256 here. What's the pressure? 577 milliliters. So I'm going to have to convert that to 577 over 760. But that's pretty close to like pressure that we have here in Woodland Park, isn't it? No, that's the volume. The pressure is 1 atmosphere. Oh, pardon me. I'm ahead of myself. All right, so P is 1. V is, so it'd be 0.577 liters is equal to N times 0.0821 times the temperature. And the temperature was 300 Celsius. Wow, that's quite high. So it'd be 573 Kelvin, right? What's N equal to? So 0.577, I don't multiply 1, divided by 0.0821, divided by 573 gives me 0.0123 moles. That doesn't sound right. Is the mass the same? is not going to work. So 1 point. All right, what do I get? So 1.57 divided by my second answer, I give 128. Okay, what did I do wrong? Guess what? It's going to be 128. This chemical must dissociate. Notice it's twice, right? See how it's twice? So this chemical, for whatever reason, there are some molecules that will break apart. What was our formula again? Back to this screen here. The fact that it's half, C7H12O2, it must actually, this is the actual molecular formula, so it must break apart into 2 ions. I have no idea what those ions would be, though. That's got to be it. That was an odd one. Okay? That's kind of a weird one, isn't it? All right. Well, we've been doing well. Lastly, we should talk about labs. What labs are they going to ask you about? The first one that they have had the most questions about over the history of the test is acid-base labs. What's an acid-base lab? Well, most likely it's going to be some variety of a titration, right? Now, a couple things in a titration. You're going to put, you have burette, right? And in this burette, you're going to add, usually you put your base up here, like sodium hydroxide, and you put some acid down here. And then you'll use some kind of an indicator, usually phenolphthalein, bromothymol blue, something like that. And as you add it, you can reach the equivalence point. One of the common questions that they might ask is about how would you find out the concentration of the sodium hydroxide? How do you find the concentration of sodium hydroxide? Via titration. Let's say that you have a bottle filled with an acid, but it's a solid acid as opposed to a liquid acid. This is standardizing NaOH. How would I standardize my NaOH? Find its, remember, standardize means find its concentration. What is its molarity? Using the fact that I have a standard acid, or I have an acid. This is called a standard acid too. What would you do? So let's say this is KHSO4. That's a common acid. Describe the experiment. We've done it. Nobody? All right. Set on the desktop. What I would do is I would add some mass of this acid. When we did this, now some of you, we kind of did it, I don't know, making some assumptions. I remember our acid-base unit, it's been a long time ago. But usually you add like about half a gram of your acid to here as a solid. And then you're going to add some water, distilled water. And then you're going to add the phenolphthalein. And you're going to add the sodium hydroxide until it turns pink. And you can molarity. Because your reaction, if you think about it, will be NaOH plus KHSO4. Now, the potassium really isn't part of the reaction, but here's our hydrogen sulfate, right? What's the products of this going to be? Huh? Water, good. And actually KNaSO4. This is all be dissociated and stuff like that, so we don't need to think about that. But the point here, this is a one-to-one reaction. If I know I have 0.5, let's say 2 grams of this, could I find out the moles of sodium hydroxide? And the liters of the sodium hydroxide you would just look at with your eyeball, right? You would read the volume. So let's say the volume it took was 15 milliliters, just for the sake of argument. So what I could do, I could say 0.52 grams of KHSO4 over 1, and I'd say grams of KHSO4 to 1 mole of KHSO4 and then I would say 1 mole KHSO4 to 1 mole NaOH. This number here is the molar mass of KHSO4, which molar mass is 104. So then I get my calculator, 0.52 divided by 104 times 1. I get 0.0050 moles of NaOH. How do I find the molarity? Divide that by what? The 0.015 liters, so, and I get 0.33. Now, are they going to make you do the math? I don't know. Some years, in the past, this year's kind of a new thing. In the past, they've made these all conceptual, so you have to describe what it would occur as opposed to do the math. I predict this year there's probably going to be a mathematical lab question. They've been itching to do that. So they might give you data on this. Another couple things about acid-base labs. How else could I know? If I gave you a graph like this, where this is pH and this is the volume, right, of NaOH, could you figure out this number based upon this graph? What would you look at? You would find this point right here, and you would look down here, and that would then be, say, equivalent to, say, 15 milliliters, wouldn't it? Could, if you had this graph, could you determine the Ka of the acid? How? Let's say the graph is very detailed instead of a sketch as mine is, but it's filled with lots and lots of, it's a well-made, lines and all that kind of stuff. So if you have this graph and it looks like this, okay, you know your equivalence point is at 15 milliliters, let's say. And this pH right here is 9.25. How could you find the Ka? You would go to 7.5. Half pH equals the pK at half the equivalence point. You would go here, and you would come back here, nice, neat, and graph. Let's say, for the sake of argument, that this right here is 4.3. What is the Ka? What's this right here? What's 4.3 going to be? 4.3 is called the pKa. So 10 negative pKa is equal to the Ka. So you would just take a calculator, do 10 to the power of negative whatever it comes off the graph, and I get 5.0 times 10 to the minus fifth. So it's very important, half the equivalence point. This is that buffer zone, right? Good? Is that ringing a bell? Now, what if you know that the pH is 9.25 at the equivalence point? What else could you know or figure out? The POH, yeah. Let's think about this reaction. You had the reaction, essentially HSO4 minus plus hydroxide. Actually, let's get on a new screen. If you've got HSO4 minus plus hydroxide, that turned into water plus sulfate, right? If you, I don't remember how this was done. The moles of this are equal to the moles of this, right? So if this is 2 moles, this is 2 moles. Nah, don't worry about it. Never mind. I was trying to think of another way to ask this question, and it's escaped my brain. Okay? That's kind of a quick and dirty how you might do an acid-base lab. Let's talk about a Thermolab. Let's just change gears. A couple of quick labs. Thermolabs, what are they going to ask you? It can't be this hard. The most common and most important Thermolab we did ever, we basically had a beaker. Okay, they may ask to do math with this, but it's not that hard. And let's say that we have magnesium and we have HCl. Have I talked about this yet? You pour them together. You can measure the change. You can have let's say that you have the mass of the magnesium is 0.10 grams, and the volume of the HCl is 100 milliliters. And what's going to happen is the temperature is going to go up. It's going to get hot. So let's go, it goes from, say, 20.0 degrees up to 25 degrees. What's delta H? What's the unit on delta H? Units tell you everything, almost. Kilojoules per mole. All right. Now we've got a volume of HCl and a mass of Mg. Which one's going to be easy to find the moles for? Magnesium. So the moles, you're going to go 0.1 grams, 0.10, and you're going to say 24 grams in 1 mole. Molar mass of magnesium is 24. So 0.1 divided by 24 is 0.004. 2. So that's your mole number. How do you find the kilojoule number? Yeah, Q equals MCAT, MC delta T. What's your mass? Right, so you have 100 milliliters of acid. But it's really, acid is going to be close to the density of water. So acid is mainly made of water, right? So 100 grams, 4.18 is your specific heat. Your change in temperature is 5 degrees. So 100 times 4.18 times 5 gives you 2,090 joules. So this is going to be, all right, watch carefully, negative 2.09 kilojoules. I did two things right there, divided by 0.0042 moles. Now, first of all, why did I put a negative sign there? Because it's exothermic released energy. The negative sign never comes from the math, it comes from your brain. Right? You have to think about it. So the math will not give you the negative answer. You have to think about it. So then you just take those numbers, divide that then by 0.0042, and you should get negative 498, it looks like. So delta H is negative 498 kilojoules per mole. Now, they may ask this conceptually. If they ask it conceptually, then the math's not all there, okay? But honestly, if they give you a question like this, and all the questions I have as examples have no math in it. So if you look at these examples in the review packet, there's no math involved. But I think now that they've kind of changed the test, sometimes they'll do a math one, sometimes they won't on sort of the lab question. So you need to kind of think. I think it's best to think through the math, even if you don't have a math question. Make up some numbers if that's helpful, because they invariably will also ask a question about error. What would cause error in this lab? Basically, the big thing is that you're going to lose energy. Okay, where's it going to go and what's it going to happen to it? You got to think through each of these error sources. And you know, sources, I forgot to talk about that with the acid base. Let's quickly talk about that. I totally spaced that. The big acid base type what? Huh? You overshoot the. All right, hold on. There we go. If you overshoot the endpoint, if you add too much volume of the NaOH, so instead of 15, you overshot the endpoint, you added 16. Well, what's that going to do to your molarity? This number is now 16 instead of 15, therefore instead of 0.33 you get a smaller number. So think about, I mean, those are the kinds of questions. Sometimes it's a reciprocal. If you add too much, it's going to make it go lower or instead of higher. Okay? All right. Let's talk about labs should we visit about. You know, a precipitation lab I think is also possible. In a precipitation lab, now we didn't do one of these. I hope Dr. Hoffman did last year. You would have two solutions. Let's say you have sodium carbonate and barium chloride. And they're both solutions. So I got beakers filled with these things. You got 100 milliliters of this stuff, and you got actually, you know a more common way they'd ask this? Let me back up. I'm going to change this a little bit. Let's say that I have a powder. This is a powder. And in there is sodium carbonate. And there is also, say, sodium chloride. These are the two chemicals that are present. Got it? What's the percentage of each? It's like this. They're both white. Sodium carbonate and sodium chloride are white powders. And they've been all mixed together. And I want to know what percentage is which. What would you do? And hint, hint, we've got some barium chloride hanging around. What happens if you add barium chloride to this? Good reaction question here. Will he react with sodium? No, they're both chlorides, right? But he will react with sodium carbonate. So it's going to make what? Barium carbonate and sodium chloride, right? So to balance this, I need a 2 here. So we ignore the salt. I believe that's it, isn't it? Yeah. So let's say that I have exactly 1 gram of the powder. That seems like a, easy thing. How would you, tell me about barium carbonate. It's a precipitate, right? All chlorides are soluble with a few exceptions, and all sodium compounds, naconoso, right? But this is a precipitate, right? So if I had these 2 solutions, if I have this powder and I want to find out what the percentage is, what would you do? They're both soluble because they're both NaS, right? I drop that powder into some water, and it would dissolve. And then to that solution, I would add barium chloride, which is also soluble. But what would you make? A precipitate. What can you do with that precipitate? Huh? How would you measure it? What would you like to know about this precipitate? How many grams? How could you find out how many grams a precipitate is? Huh? What's this solution going to look like when you add the barium chloride? Huh? It's going to be cloudy. It's not blue, by the way. It's going to be white cloudy. It's going to be cloudy. So what could you do with this solution? Draw on here. What's here? Filter paper? You ever done this? Filter paper? Okay. Oh, well, my last class will next year they'll know how to do this. Okay, but you're learning it now. All right, you'd have a piece of filter paper in there, right? And as you pour this in here, what's going to stay on the filter paper? The precipitate, the barium carbonate, and then the rest of the stuff's going to flow through. So you collect it on a piece of filter paper. Now, what do you probably need to do with the filter paper? You need to dry it because it's now wet, right? So you just would dry it, put it in an oven overnight, or just let it dry overnight, or whatever it takes. You would dry it, and you could then find the mass of the barium carbonate. Got it? Once you know the mass of the barium carbonate, you would do a very simple stoichiometry and go gram problem to gram. You would say, let's say that it produces, I better pick a number that would work. Let's say it produces 0.5 grams of precipitate. What is the percentage of sodium carbonate? Well, you'd say 0.5 grams of barium carbonate. And then I would say grams of barium carbonate, 1 mole of barium carbonate. The ratio is 1 to 1, so 1 mole of the sodium carbonate to 1 mole of the barium carbonate times grams of the sodium carbonate to 1 mole of the sodium carbonate. I'm out of space here. I need to find out these 2 numbers. What are the molar masses of my 2 compounds, which I haven't figured out yet? So 137 is barium, plus carbon, which is 12, plus 16 times a 3. So the first number here is 197. And this next number is sodium, so it would be 23 times 2, because there's 2 of them, plus 12, plus 16 times 3, gives me 106. So I take 0.5, divide by 197, times 1 over 1, times 106. And I get 0.269 grams. What percentage do I have? Easy to know. Your percent will be 0.269 over 1.00, which is 26.9%. All right, error question. What if your filter paper is still wet when you weigh it? So this number, this 0.5, is too big. So the number that you put into this calculator, instead of 0.5, it really should have been some number like 0.4. Therefore, your percentage here would be too high. What happens if when you are pouring it down, you're pouring it out, a little bit of the solution spilt onto the table?
then the grams that you collected, instead of being 0.5, you collectively should have collected 0.6, right? Because some of it is on the table or possibly went down the drain or something like that, right? Then it's the opposite effect, isn't it? So you want to think about those kinds of questions. All right? Good. Now I handed out, I'm just going to be a bit random here today. It might not be a bad thing to go looking at. There's the big exam, remember you were looking at. Very in it. I handed out to you terms you should know. Do you all have that? Key terms and colors you should know. Anybody have that in front of you? Or Mitch, can you look on? Come on, Colton, help them out. One of you guys need to move so you can be next to somebody. Are there any ones of these comments or these terms that you do not know? Everybody know what an activated complex is? What's the activated complex? That's kind of a hard one, the first one. All right, in an activated complex, this is what an activated complex is. Remember, we have these graphs of reaction progress, where this is the reactants and this is the products. By the way, is this an endothermic or an exothermic reaction? It's kind of barely, but where this is energy and this is time, or reaction progress, we would say. And this number is here, and this number is just a little bit lower than that. This is delta H, this distance here, and so it's going down or up? It's going down, so therefore this is exothermic. Okay, the activated complex is the substance up here at top. That's the activated complex. Or we actually have called it, the other thing, it's intermediate. We've used that term. That's the same thing, saying the same thing. Oh, amphoteric means something that's an acid and a base. Classic example of that is water. Water can be an acid and a base. Bronsted-Lowry acid-base. Okay, good. Don't worry about the Haber process. That's related. Adsorption is a catalyst. You know, I haven't seen that on years on tests. Let's not worry about adsorption. Coordination compounds, that's a complex ion. So if I've got copper, 2 positive plus ammonia, makes CuNH3, 4, 2 positive. That's called the coordination compound. Or sometimes the complex ion or coordination compound, same thing. Everybody know what electron affinity is? Kind of halfway down the first column there. Energy associated as you add an electron. It's the opposite of ionization energy, right? How about fission and fusion? What's fission? Breaking apart, good. Fusion? Bringing together. And what are you breaking apart and bringing together? The nuclei of atoms, right? All right, all those different, those are Hund's rule and the Aufbau principle, the Azimuthal quantum number, the Pauli exclusion principle. Frankly, I get them mixed up. It's basically, there are several rules on quantum numbers, right? You fill the lowest energy level first, and then they don't double up. You know, if you've got a p orbital, you go like this before you double up, right? And that's one of those. And then, yeah, they all have a different name. There's sort of different rules of how you fill electron orbitals, and I get them mixed up. It's more important to know the rules than it is to know the names of the rules. But it wouldn't hurt. They might have a question on that. But which one they'd pick, I wouldn't know. Principal quantum number is N. Speaking of quantum numbers, we haven't talked about that in a long time. Those tend to find multiple choice test, right? If I've got, what is quantum numbers? You've got N, can be 1, you know, comma 2, comma 3, etc. And L can be what? 0, 1, ... to n minus 1. And m sub L is from negative L to positive L. And then m sub S is positive 1/2 or negative 1/2. Remember, these are like the address of a particular electron, right? And so, and L is the one everyone has to watch at. If L is 0, it means it's an s orbital. If L is 1, it's a p orbital. If L is 2, it's a d orbital. And if L is 3, it's an f orbital, right? So if I have, let's say, a cadmium atom, cadmium element number 48, what is his outer electron configuration going to be? Well, give me the shorthand notation of cadmium, starting with the last noble gas. Krypton, good. 5s2, 4d10. All right, now, give me the address of that electron. So what is this box here? The 4d box. So what is n? 4, because 4d, right? What is L? 2. What is m sub L? Negative 2. Remember, this is negative 2, negative 1, 0, 1, 2. And then m sub S, hard to say. That would be an acceptable quantum number.
So 1/2 negative 1/2 due to rotation.
Yeah, the electrons are spinning, and they spin in opposite directions in a particular orbital. Which is which? It's arbitrary. At some level, when I say that this box is -2, that's a bit, depends on how you're going to label it, but I think it's easiest to understand it this way. But that would be an acceptable for this electron. So that's a good quantum number thing, something we haven't talked about, like, seems like forever, right? You know, have we talked about the Tyndall effect? Almost the last one there. All right, the Tyndall effect is actually an interesting thing. One thing we didn't, did we? Some of these things that sometimes we miss on time. Okay, if you take light and you pass it through a solution, it'll go right on through. Okay? But if you take light and you pass it through a colloid, what you're going to see is the light will be reflected as it goes through. You ever seen on a sunny day and there's dust in the sky, or there's dust, say, in your house, and as the light comes through your window pane, you can see the beam of light? That's the Tyndall effect. It reflects off of the dust. But the light that comes from the sun, typically you look up and you do not see the beams of light, do you? You just see the light lit up, the reflection of the light. And so if you have a colloid as opposed to a solution, have you heard the word colloid before? Okay, some of you have and some of you haven't. A solution, of course, is what we've been talking about, like, water, there's salt water and all that kind of stuff. A colloid has slightly larger particles. See, milk is a colloid. And so they would reflect. The milk's almost too thick to probably do this. But if you shine light through milk, real bright stuff, it would light up the milk. All right. So this is called a colloid. These have itsy-bitsy tiny particles, and these have bigger particles. Now, they're not so big that you can see them with your naked eye or something like that, but they're big enough that they'll be reflected by light. What about this term? I'm just jumping around here. The mass defect. What does that refer to? What does the mass refer to? What topic is this? This is nuclear chemistry. What's the mass defect? That's your hint now. Mass defect, anybody? Remember, if you add up, go ahead, Eric. If you take 8 protons, find their masses, and 8 neutrons and find their masses, and add them together, you would expect that their mass would be 16. Right? Because protons and neutrons weigh 1 atomic mass unit-ish. Right? Turns out they weigh less together than they do apart. And then that mass is converted into energy, according to Einstein's equation, equals mc squared. This is why you have so much energy in a nuclear reaction, because there's some mass lost. So when you take the nuclei, let's say fusion, you take two nuclei and whoop, jam them together. This weighs 1, this weighs 1, and you say 1 plus 1 equals 1.98. Right? And that 0.02 is converted to energy, and you get lots and lots and lots and lots of energy, because you're taking it and multiplying that mass times the speed of light squared. And the speed of light is a big number, and when you square it, you get a really, really big number. Okay? That's where all the energy comes in nuclear reactions, because of the mass defect. Okay? True in a fission reaction, too. They break apart, and the products weigh less than the reactants. And that energy, and then it's converted into obscene amounts of energy. Ionic bonding, ideal solution. Oh, how about ideal solution? Ideal gases. I'm just obviously just random here. Tell me about an ideal gas. I'm talking conceptual now. What does that mean? The key thing, one very important, no attraction for itself. Yeah, the ideal gas law is PV equals nRT, but it assumes that the molecules, so if I have a molecule of oxygen and it's flying around at about 1,200 miles per hour, remember, another molecule of oxygen, when they go past each other, they do not attract to each other at all. All right? If the molecules like each other, then it's not going to behave in an ideal fashion. That is the main tenet of the ideal gas, of understanding that, conceptually. Okay? All right. Other topics. This is something I wanted last time, but you're going to start your test next time. But there, we only have so many days left. What we got Friday, Tuesday, Thursday, Monday. So we basically got a test on 2 days. We only have 2 class days left, right? So, and what I'm going to do is I'm going to visit with you on the second time next week. So Thursday next week, I'm going to hand you back your AP exam and say that you got a 5, a 4, a 3, a 2, or a 1. Hopefully there's none of the ones. And I'm going to say this is your score based upon the class. Now, that's good, but what I want you to do is to think through. You're going to also kind of evaluate yourself and say, but I really don't understand acid-base equilibrium problems. I better get on the stick. But with that said, are there particular topics? One thing I want you to do for homework tonight is I want you to bring me a list, and if you want to even email it to me tonight, for all that matters, of things that you would like me to podcast. All right? Would you like me to do more reaction stuff? I think, and that's probably one thing I'm hearing. I had another sheet and I lost it, and then I emailed to get it again. But I could podcast some more reactions and just go over that, because obviously we're running out of time, but I can easily podcast it, and then you can watch it at your leisure at home with a paper in front of you or whatever it takes. So, or is it acid-base equilibrium? So I'm hearing reactions, acid-base equilibrium, right? Maybe? Actually, let me show you something. This is just good testing strategy. How do I train for triathlons? Okay, let me tell you a little bit about myself. When I was in high school, I was a competitive swimmer. I got 10th in the state of Oregon in the 100-yard butterfly, and I was on a relay team that got like 3rd place. I was a very good swimmer. Too short to make it really big time in college, but I was a good swimmer. Okay? All right? I have acquired a pretty decent skill for biking, where I am quite competitive as a cyclist, and I really suck at running compared to people, that I race against. Okay, now, you know something about me. I have a strength, a weakness, and something that's, kind of a moderate strength. All right, you're my coach. What do you tell me to do? Run a lot, right? If I want to be fast, I need to run. Should I swim a lot? No. Okay, so that's how I train. How do I race? How do I race? The point is here, I'm making to it. you train your weaknesses, you race your strengths. Make sense? All right. So that I can improve my weak point, I've got to run a lot. To race, I should race my strengths. So frankly, if I want to win the race, if I want to do well in the race, I've got to be first or second out of the water. For old farts like me, anyways. Okay, those are young kids I don't care about. And then on the bike, I got to hold my own, and then I pray someday I'll be able to like run fast enough to hold on to the lead. I'll never win a race, but I'm too old and too slow on the run. But the point is that's true for you too, isn't it? Okay, you have strengths, and you play to your strengths. If there's a section that you know you really are weak on, you need to work on that now, so that you can get some points in the test on that. But if you know you're strong in thermodynamics as opposed to acid-base, then you need to take the test for your strengths. This was more applicable in the old days when you had choices. But now there are no choices on the test. So it's just an emphasis on how you look at the exam. It's a good way to think about how you're going to prepare yourself for the exam. Okay? What's your weaknesses? Figure out what your weaknesses are. Train for those or study for those, as in our example. And then when you take the test, also on the test, we should talk about other things on the test. Test strategy. We've got some time, perfectly. On the multiple choice, you lose 1/4 point for each wrong answer. So let's say, there are 75 questions. So let's say that you answer 60 questions total. Of those 60, you left 15 blank. You answered 40 of them correctly, and that means that you got 20 wrong. Your score will be 40 minus 1/4 times 20, and 1/4 of 20 is 5, so you will get 35 points. Here's my recommendation on multiple choice. Read the question. Actually, I've got a couple of recommendations on multiple choice. There are always 5 choices, A, B, C, D, E. All right? So you've got question right here, and you've got A, B, C, D, E. If you make a guess, you have a chance. What's your chance? 1 in 5. Good idea? If it's a total like, I have no idea, C! It's got to be C! Because it's mostly C. No, don't go that. Don't do that. Okay. All right, let's say, so obviously, don't just, if you read a question, I think there's 3 kinds of questions. There are questions that you know. Obviously, you answer them. Check, I got it. There's close that you have no clue. You see a no clue question. Here's my recommendation. Put an X through it and just don't worry about it. Just skip it. You are not even going to even think about that question again. Please, but you can't do this to 45 questions. Or you won't get a good score. All right. But I'll say it, even Eric is going to have a couple of questions he's going to have no clue on. Right? It's okay. All right. And Eric needs to just, some of you have a deep, deep problem with leaving blank questions. It bothers your psychological profile or whatever. You need to just get over it because your goal is to score on this test. And you don't want to just be guessing. And then there's third ones, I call them the time questions. I especially see this like if you got to say balance this redox reaction. That takes a lot of time. Okay? The time question, put a big T next to it, unless you're ahead of the ball game. Now, guys, there's 75 questions, and there's 90 minutes. Please bring with you a digital watch to the test. You should do this next. This is on, we're taking the choice on Tuesday. Take a digital watch. If there's 75 minutes, or 75 questions in 90 minutes, that's roughly 1 minute per question, right? And answer the questions in order, 1, 2, 3, 4, 5. And when you get down to question number 25 or something like that, and you look at your watch, and if your watch says 25 minutes, then you're on schedule. You have time to do the T questions. Got it? But if you are behind, you're at 25 questions, or let's say you're at 25 minutes, you're at question 15, you need to skip the time questions, and if you can maybe pick up some time later on, you come back to them. Okay? Now, mathematically, when should you guess? I think you need to eliminate 2 of them. And then you know it's either A, B, or C, or whatever. You know it cannot be D or E. You've convinced yourself. Yeah, it isn't necessarily always true, but you've convinced yourself that D and E it cannot be, and then you go ahead and guess. Okay? So those are some things to think about. Now, don't panic. The good news on this test, there's 160 points possible on the test. A 5 is 107. Take 107, divided by 160, that is 67%. And actually, when I say 107, the reality is it varies. How do they actually grade the test? Every year, they rank them from the top guy to the bottom guy. And they've got 30,000 tests here. And they just draw the line. If for 1 year that the test is particularly easy, then this number might go up to, say, actually 107 seems like a high. It might go up to 110, 112 or something like that. Or if it's a hard year, I've seen it down as low as 99. But because sometimes the test is harder. They write the test, and it's hard to say what scores are going to be. So where they could draw that line is going to vary each year. So when I say 107, actually that seems kind of high. I think usually it's like 104. And so it goes up to maybe 110 and down to 99. That's kind of where the 5 range is. And there's a similar kind of a line for a 4 and 3 and everything like that. So you're not expected to know everything, and you can still get a 5. So don't think that this is a total mystery to anybody. Yes, apparently there are, and there's been some discussion about it happens once every couple of years. It doesn't happen every year. So, but I understand that the perfect score kids, it happens once every couple of years. You'll get 1 or 2 people. It's a pretty rare occurrence to get a perfect score. So, well, no, they don't, but there's been some talk that they ought to. Because frankly, there's some subjects that I have skipped because of time. We haven't talked about the molecular orbital theory. If you ever see anything on the molecular bonding and anti-bonding, you need to skip that. Or we call paramagnetism and diamagnetism. It's in chapter 9, by the way, Eric, if you want to read it, okay. So it would have taken us a block and a half at least to discuss this. And it literally would be 1 multiple choice question on the test, maybe 2. So it was one of those strategic decisions I made, is it worth that much time given the fact that we also had numerous snow days and everything? No, it wasn't. Okay, so it's the second half of chapter 9 that we didn't cover. Okay, and it's a very complex conceptual thing. Okay, other questions? Your homework tonight is just to study everything. I mean, folks, and I haven't been checking your homework like I have in the past, but I really think what you ought to do is spend your time tonight. Get your note cards done. They're due next time, so that's certainly, you want those extra 100 points, extra credit points. Get your note cards done. I'll be checking those during the exam. You want to really just study. Pretend like the test is this Friday, and then you'll know better, even though it's 2 weeks from yesterday or whatever it is. Okay? You guys are doing great. Work hard. It's not over, though.